Sure. Let's wait some few minutes more. Campus e particulars of from Universidad Nacional de Colombia, the branch of Bogota. Today we have the immense pleasure and honor to have with us Hofie Holmfridur from the Institute for Advanced Study in Princeton, the School of Natural Sciences. And Hofie was did his her studies in Iceland, undergraduate studies, PhD, master and PhD in Harvard, and she's currently postdoc in Princeton, in the Institute for Advanced Study in Princeton. And today she will talk us about crossing behind scattering amplitudes. Please, thank you so much again.
It's really a pleasure to give this talk. And yeah, as I was saying earlier, presumably now you can see my full screen, but I can't see anyone. So feel free to unmute yourselves at any point with questions.
Thank you so much.
Yeah, and I'm very happy to present this work, which came out in the fall in collaboration with Simon Coronhuo, Mathieu Giroux, and Sebastian Misera. So here's my outline today. I'll start with an introduction, basically about what crossing symmetry is. And we'll see that for 2-to-2 scattering, so for a scattering of 2 incoming particles to 2 outgoing particles, it's a well-studied problem since the 60s. But as we go to higher point scattering, for example, 2-to-3 particle scattering, it was really almost unexplored territory. And what we'll find when we start looking into that in the introduction is that we'll actually be forced to look at more general observables than scattering amplitudes. So that leads us to part 2, where we'll talk about what is this more general class of observables, or what can be measured asymptotically, as it's titled here. So one of those observables will be the gravitational waveform, which is basically the gravitational wave that a detector on Earth, such as the LIGO detector, would detect after scattering of black holes. So we'll take a little bit of detour in part 3 to talk about how to compute those observables and their physical properties, which are, to me, an interesting which came about kind of as a byproduct of the story, but is very interesting in its own right. So we'll devote section 3 to that. And then in the last part, we'll get to crossing itself, and in particular, how crossing relates these different observables to each other. So let's start with a review on crossing symmetry. So crossing symmetry tells us that the scattering amplitudes for some processes, let's say AB to CD, and the cross process, which I've labeled here as AC bar to B bar D, are boundary values of the same analytic function. So more precisely, on the left here, we have a scattering amplitude for AB going to CD. And what we do is that we cross particles B and C, meaning that we take C to be incoming and B to be outgoing, and turn a particle into an antiparticle. And crossing symmetry tells us that the 2 amplitudes for these 2 processes are analytic continuations of each other. Let me emphasize that this is a different condition from relabeling or cyclic invariance. Sometimes crossing symmetry, the term is used for different things. But here we really mean the sense in which is written in this equation here, that it's an analytic continuation. The 2 amplitudes are analytic continuations of each other. Let me also emphasize that this is not a CPT. CPT would be taking all outgoing particles to be incoming and vice versa. But anyway, the argument for crossing symmetry is often stated as the fact that particles should be indistinguishable from antiparticles traveling back in time. But I've deliberately put a question mark here because this is precisely the point that we're going to revisit in this talk. But the important thing to know about crossing symmetry is that we like it partially because it would allow us to use results from previous computations. So let's say we've computed the left process here, E plus E minus to gamma gamma, to any loop order, 1, 2, 3, or even 120 loop orders, or non-perturbatively, then we could get the right amplitude here simply by an analytic continuation, which is usually much simpler than starting over again and computing the amplitude from scratch. To drive home how non-trivial this is, crossing symmetry tells us that if we want to study how an apple falls to Earth, then that's a scattering process between the apple and the Earth. But crossing symmetry tells us that we might as well study the process Earth anti-Earth going to apple anti-apple. And we could study how an apple falls to Earth via that process. So that's an entirely crazy idea to me, but I think this example really drives home how non-trivial crossing symmetry is. It's not really something we should take for granted. But let's also talk about what's known about crossing symmetry. And let's start talking about, or keep talking about 2-to-2 scattering processes. So for 2-to-2 scattering, crossing symmetry was proven for the non-perturbative amplitude at fixed momentum transfer, t less than 0, in theories with a mass gap. So what we have in mind here is some amplitude like this one, Compton scattering E minus gamma to E minus gamma. We define S as the incoming center of mass energy squared, and we define T as the momentum transfer. And this plot here is in the complex S-plane. So the physical amplitude is, of course, for real values of S. So in the S channel, it lives somewhere up on this real S axis. But what was shown in the 60s by Burroughs, Epstein, and Glasser is that there could be some singularities in the complex plane of this amplitude, but they're confined to this shaded region. So basically, there's a bounded region in which we can have singularities, which are also sometimes called anomalous thresholds. But since this region is bounded, it means that there exists a path of analytic continuation in the unshaded region, which gets us to the other side of the amplitude. And actually, because we're approaching the negative S-axis from the upper half plane, this is actually the conjugated amplitude in this case. And this is...
Excuse me, the singularity in the gray region are coming from unitarity?
So that's actually a good question. Actually, we don't know about any singularity in the gray region. So the unitarity singularities would be on the real axis, where this branch cut is drawn. And it's still an open question whether there are actually some theories which exhibit singularities in the gray region. But there is a proof that there is a bound on the region in which there can be singularities. So that's currently the only thing we know. The only thing we know is that we don't have an example of a singularity in the gray region. And we know that there can't be any singularities outside of it.
But of course, if one is using, for instance, some method coming from Feynman diagrams, perturbative methods, in procedure like tensor reduction, or I mean, these spurious singularities can happen, and so
absolutely
they should come in this gray region there, huh?
Yes, but the thing is that we've not found them to be complex, not on the physical sheet. So if you cross this branch cut, then you'll see singularities here all over. But as I say, it's still an open question whether it actually occurs on the physical sheet. And we don't know the answer to that. As I say, it's an open question currently, but yeah, definitely if you start solving for the singularities, you'll find on the second sheet, you'll find them all over here in this gray block.
So the unitarity singularity are just those on the real axis.
Exactly. And we don't have a bound on those. There could in principle be singularities on this whole axis.
Okay.
So we don't try to cross the axis. We just try to go to large enough S and then take this kind of big arc between the two. Yeah, so let's now extend this plot to the lower half plane as well. Yeah, so I was just saying, we don't know if there is an opening here or not. Sometimes there is not an opening, but in any case, we can write down the amplitude here in the S channel, and the conjugated amplitude, which lives kind of on the other side of the branch cut. And then similarly in the U channel. So for negative S, since we're fixing T, we can solve for U. And the U channel physical region amplitude will be here for negative S. And then we have the conjugated amplitude on the top. And similarly in the lower half plane, we have kind of the mirrored picture of what's going on. But it's actually important in this story, and I want you to remember this, that the natural thing that happens for crossing is that an amplitude crosses to a conjugated amplitude. And then for 2 to 2, we can kind of just do this move once more. We can now just fix S and do a continuation in U or T to kind of get back to the, in this case, T channel amplitude and not the conjugated amplitude. So the natural thing to do would be to try to extend this for the 5-point amplitude and ask whether it's true.
Excuse me, I mean concerning the slide before.
Yeah.
You got the T channel after you pass the branch cut.
No, so you just do one more rotation like this. So you basically now fix S and you can do a continuation in U. So you start with this one and then you end up on the amplitude itself, if that makes sense.
I mean, to get back to the same amplitude as before, which was in the Compton effect.
Exactly. So now you can just do a couple of moves to basically get this correspondence here.
But to get the pair annihilation, it just make one rotation in the upper plane and then go down to the branch cut.
So we never cross the branch cut on the real axis because we don't know what happens then. Instead,
I mean, adding the imaginary part. You know.
So we never, so basically we use another kind of move to go off in a different complex plane starting from this one. So we never go directly between these two, if that makes sense.
Okay.
Not in the S plane. So the argument is basically that with one crossing move, you get from an amplitude to a conjugated amplitude. And then you can use one more crossing move either in the complex T or the complex U plane to get back to the amplitude. Does that make sense?
Yes.
Yeah. But that's an excellent question, and that's an important point, that we're always kind of restricting to these slightly complex values. So we're not crossing the real axis just because we don't have a good handle on what happens.
But one knows that there is the jump given by the imaginary part there.
Absolutely, but then it would not be an analytic continuation. No, then it would be a jump. Exactly.
Okay.
Mm-hmm. Exactly. Good. All right. So the natural thing to do, and I think at least I would have assumed this a couple of years ago, that for the 5-point amplitude, we would just do the same, that we would have, let's say, E minus gamma to E plus E minus E minus. And if we cross the positron and the photon in this case, then we would get back something like the conjugated scattering if we do a similar crossing in the upper half plane, just like we got for the 2 to 2 amplitude of E minus E minus to E minus E minus gamma. But you might have guessed from all the question marks on this slide that the answer is actually no. And that's the whole point of this talk, is to figure out and present to you what is the result of analytically continuing scattering amplitudes for going beyond 2 to 2 scattering. So for example, for this 2 to 3 scattering process, what happens if we do an analytic continuation in a variable that I'm going to call z? And the only thing you need to know for now about this complex z variable is that it has the effect of precisely changing the photon and positron from being incoming to outgoing. So to understand this better, let's do a simple example at tree level. And it might seem entirely useless to do a tree level example because we just have poles and we can always analytically continue beyond poles. But it's actually very useful for us to use these tree level examples with the correct I epsilon prescriptions for the propagators to understand what goes on at the loop level. So we'll go to loop level later, but for now, let me just present this simple example because it's easier to understand.
But this is in fitting the cube theory, no?
Yes.
It is not, I mean, you don't need the prescription for the numerator.
Exactly.
Okay.
So the numerator kind of goes along for the ride in this story. So what we'll actually do in the end is to do something similar to what we discussed earlier, to use tensor reduction and kind of prove crossing at the level of individual master integrals or individual integrals in the bases. And it's not so hard to show, and it's in our paper that the numerators kind of go along for the ride in this story. But yeah, for now we're just doing scalar theories because it holds more generally, but it's easiest to understand. All the meat is in the denominators anyway. All the complications are in the denominators. Yeah, so let me also introduce a few conventions that I'm going to be using throughout the talk, and I already started using this, that the particles that will cross will always be in red. And moreover, to match onto our conventions for operator ordering, which we take to be the standard textbook convention, which we'll use in a minute, we'll actually start taking time flowing to the left. So that's a bit counterintuitive in the beginning, but hopefully the arrows will help. In any case, what we're going to do here is that we're going to start with this amplitude where we take 1, 2 to be incoming and 3, 4, 5 to be outgoing, meaning that 1, 3 is actually space-like, S1, 3. So we start with a negative S1, 3. And we rotate S1, 3 in the lower half plane at fixed S4, 5. And this might seem a bit ad hoc right now, but it exchanges particles 2 and 3 if we do this rotation at fixed S4, 5. And we'll see later why this is motivated. For now, let's just try to do it and see what happens. So we expect from the previous picture, remember, that if we do this rotation for the 2 to 2, we should get back the conjugated amplitude. But now let's just do the computation. We start with this expression up here for the tree level amplitude. And we take S1, 3 to be analytically continued in the lower half plane, but we keep S4, 5 fixed. So S4, 5, we put a tiny positive imaginary part to that one. But S1, 3 will pick up a tiny negative imaginary part. So this object on the nose is not really a scattering amplitude. It's not a scattering amplitude and it's not a conjugated amplitude because it has this mixed I epsilon prescription, one positive and one negative. But we also know that we can rewrite it in terms of the conjugated amplitude, which is kind of the result that at least I would have naively expected before starting to work on this. But then we have to compensate with this delta function term, or this kind of cut integral term, which is like an amplitude times the conjugated amplitude. So we have one of the propagators having a negative I epsilon, but then we cut this particle here. But for now, the crucial takeaway point is that after the analytic continuation, we neither land on an amplitude nor a conjugated amplitude. The takeaway point is that the analytic continuation from the amplitude at 2 to 3 points lands us on something new. And that's what we're going to try to understand in this talk. But the cool thing is that this new thing is not some random object that's just an analytic continuation of the amplitude. It's actually a different observable. So we'll learn that scattering amplitudes are part of a larger family of observables that are related by an analytic continuation. And the crossing equation is our term for what describes the result of the analytic continuation. So I've shown you one example here, but we'll start the talk with kind of going through what these different observables are. And then, as I said in the last part, we'll talk about what this equation actually means, how they're related by crossing.
And excuse me, the cuts of the dashed line are in
Yeah,
the same
yeah,
sense of the delta function
exactly.
of the on-shell condition that you put to the.
Exactly. So in this picture, and we'll go over this later, excellent question. These orange cuts mean precisely just the same thing as happens in the unitarity cuts or the Kutkowski cuts, that we put all of the particles that flow through the cut on shell with positive energy.
Mhm.
Exactly.
But I mean, in Katkowski, you aim at finding the imaginary part. Here not.
Exactly.
Here not.
Here not. And it's different also, yeah, we'll talk about it more later. But it's different because it's kind of mixing, you can see it from this equation here, that these terms are kind of mixing scattering amplitudes and conjugated amplitudes in different ways. So it's definitely different from Kutkowski, but the phase-space integral is the same one. This
Okay.
orange cut is labeling the same kind of phase-space integral.
I mean, S is the S operator.
Yeah, the S matrix. Exactly. Okay. Before we go on to the next part, let me just tell you a tiny bit about the history of crossing symmetry. So it's a very old idea. It was proposed for quantum field theory in 1954 by Gell-Mann, Goldberger, and Turing. And it's proven for non-perturbative 2 to 2 and 2 to 3 scalar amplitudes in the series of papers by Brose, Epstein, and Glasser in the 60s, and then by Brose in the 80s. And these are extremely technical proofs. If you try to go through them, they're collectively hundreds of pages, and they really use mass gap, causality, and unitarity as physical principles. But then, very importantly, there is a part of the proof that uses so-called analytic extension theorems, meaning that they use theorems that hold kind of for any analytic functions, not specifically for scattering amplitudes and not specifically for amplitudes satisfying any physical principle. So they're very challenging because they kind of don't assume, in this last step, they kind of don't assume anything except that the function is analytic in some region. So that's actually one of the interesting points that we're trying to work on now, is how can we input physical principles to gain some better handle on crossing symmetry, which is this last point.
And so the 2 to 3 amplitudes was analyzed by them.
It
So
was.
they found something similar to your result?
Yes, they did. That's actually an excellent question. And we think we had the, so we agree with everything that they do, of course. And we think that part of the advantage for us was basically realizing that what they had found in these papers on 2 to 3 was actually different observables. So what they thought at the time was just that it was some random analytic continuations of the scattering amplitudes that didn't have any physical interpretation. So that's actually, yeah, one of the points that we're very interested in is precisely understanding this connection between crossing and physical principles.
But for sure, in the case of scalar amplitudes, they don't have, I mean, your interpretations in terms of waveforms, all this stuff. I mean, it's the scalar legs on shell are just one. I mean, so
absolutely, yeah, we're going beyond those, but yeah, I also want to acknowledge that we learned a lot from those papers as well. So it was, yeah,
and for sure, they, since you mentioned the mass gap, they don't have infrared divergences.
Exactly. So that's an excellent point, and I'll talk a lot about infrared divergences in the next sections. Let me actually just go to the next outline. So especially here in part 3. And let me also mention that we took a bit different approach to these 60s paper, in the sense that we wanted to kind of ask the first question, which is what happens as we do this analytic continuation, provided that it exists. And what they do is that they prove rigorously with these hundreds of pages that it actually exists. But we took a much more pragmatic approach, which was basically, okay, we have this proposal for what can happen, And let's just go and check it. And let's just go and check it, for example, for all one-loop master integrals is something that we did and we're just able to do for massless theories as well. So then we don't have to ask the questions of what happens for infrared divergences, etc., because we know that it holds in dimensional regularization. But that's actually one of the follow-up works for us, is trying to prove this equation non-perturbatively. But at least I think for massless particles for now, the best hope we can have is to prove it at the level of in dimensional regularization, I should say. So that the object is well defined to begin with.
Okay.
But that's, of course, a very important point, and especially for phenomenological purposes, to have a handle on what happens for massless particles. Okay, yeah, so that was the introduction about crossing symmetry. So let's now go on to asking the question of what can be measured asymptotically. What are these different objects with these different I epsilon prescriptions that we're landing on? So here is the algebra, the asymptotic algebra that we assume. So these are things that we take as axioms, basically. That we have an algebra of asymptotic measurements in the far past and the far future. So we have the usual commutation relations between creation and annihilation operators. Let me also mention that in textbooks, we usually write these as A in and A out, but we're going to call the creation operators in the past A's. Those are the ones usually corresponding to A in. And the creation and the annihilation operators in the future, we're going to call them A out. We're going to call them B, but in textbooks, they're usually A out. And the reason for that is that we're going to start writing down long strings of these creation and annihilation operators. So it just gets very, very cluttered if we have these superscripts and subscripts and daggered and undaggered, etc. So just remember that A is in the past and B is in the future.
Of course, you are in the Heisenberg representation.
We are, yes, exactly. We're in the Heisenberg representation, and that's part of point 2 here, that we take as an axiom that these operators act on equivalent Hilbert spaces and that they're related by a unitary evolution operator. And so B is given by S dagger AS, and similarly for B dagger. And we also assume that S is unitary, so S dagger is 1. We assume that there exists a time invariant vacuum that we call 0. So S leaves the vacuum invariant, and the annihilation operators annihilate the vacuum, as usual. The last point, point 4, is actually a very crucial one. It's stability, so let me try to explain that. So we assume that if we have a one-particle state, AI dagger acting on 0, then nothing can happen to that state until it interacts with another particle, basically. And this means that S acting on a one-particle state is the same as the one-particle state itself. And similarly for the future operators.
So, I mean, you have in the Heisenberg representation, your states have all the information about all history of the system. So from minus infinity to plus infinity in time. And I mean, these axioms are compatible with the fact that the S matrix elements are the overlapping between out and in
exactly.
In states. So they are the usual in and out states.
This is just I'm here just reviewing the standard formulation in the Heisenberg picture. There is nothing nothing fancy going on. Yeah.
What somehow seems to me that is new is the fact that for you all particles are stable.
That's an assumption in this work. So if they're not stable, what the crossing equations will have to be modified.
Okay.
So we're assuming that all particles are stable.
So no Higgs, no
No, I
no.
mean, yeah, we have some ideas about how to incorporate that as kind of a
Mm,
composite particle or representing it by a composite particle. But for now, let's just, at least for simplicity, take all particles to be stable.
okay.
Yeah, let me also mention that we assume both Fermi statistics, flat space, and Poincare invariance. And you can try to go away from these assumptions, and there has been some recent work on that. But again, for simplicity, this was the case that we started with. So using this algebra, what can we measure asymptotically? So let's start at 4 points. What can we do at 4 points? We have 4 particles, 1, 2, 3, and 4. And one thing we can do is that we can string them together like this. We can act with creation operators in the past and annihilation operators in the future. And remembering that B is S dagger AS and B dagger is S dagger A dagger S, then we can rewrite this as an S operator going from 1, 2 to 3, 4. So if we work in the basis of instates, for example, this is just the usual S matrix. So we can view it however we want. On the left, far left here, this is kind of, as we talked about, the overlap between the instate and the outstate being given by these B operators in the future acting on the vacuum. We can also act with B dagger first and then A. This gives the conjugated S matrix for 1, 2, 2, 3, 4. And then we can act with only A's. This is like a forward term. And we'll also take these to be 0. So we'll always assume that none of the incoming particles is exactly forward with any of the outgoing particles. And here we can see why we take time to flow to the left. It's because we'll use these pictures in operators a lot. And it gets very confusing if we use the traditional convention of basically time flowing to right. So we always have to reverse the operators with respect to the pictures. So we had to choose one convention, and we decided to change the convention for the pictures. So time will flow from right to left.
And I mean, back to the slides before.
Yeah.
The
Sorry.
next.
This one, yeah.
Yeah. The external legs are not free states.
They're not. Here,
Are in states.
This is completely non-perturbative. Yeah.
So S is not the given by the Dyson series.
Not necessarily. We can use these relations order by order in perturbation theory, but the 60s proofs are all for the non-perturbative amplitude. The argument that we have here is also non-perturbative. So we work in this Heisenberg picture framework where everything is.
So usually one in the courses takes the S matrix sandwiched between free particle states, but here not. They are between in states. Where
exactly.
all the story is present there. I mean,
exactly. So we
it's
don't have
it's non-perturbative.
It's non-perturbative.
In the blob, there is everything.
Everything, exactly. Everything. All right. So at 5 points, what can we do with the same algebra? We can write down again the S matrix and the conjugated S matrix.
Sorry, again, at the 0 in the slide before are due to the stability, the conditional stability.
It's not. It's basically an assumption. It's an assumption that one is not exactly forward with 3 or 4.
I see. Okay.
So then we can just act with these on the right here. Because we assume that we can always commute A operators by themselves and B operators by themselves, but we can't commute an A with a B, if that makes sense. So yeah, take the 0 as an assumption. All right, but at 5 points, this is not actually the only things we can write down, because now we can write down things like these terms here, where we have A dagger, followed by a B, followed by an A, and then an A. So basically what this means is that we have kind of an expectation value of a B, of a future operator, in the background of past operators. So we can again play the game of writing B as S stagger AS and insert a complete set of states in here. And then pictorially, what we get is this not quite amplitude, not quite conjugated amplitude object on the right here. So here we've inserted a complete set of states X and integrate inclusively over phase space. So that's what this X blob or X shading means here. But note that we can't collapse the S stagger here by unitarity because they're not just connected by this X, they're also, the S blob also has this outgoing particle 3. So we can also view this as a scattering amplitude for 1, 2 going to 3 and anything else, and then a conjugated amplitude for that anything else to go to 4 and 5. So if 3 were not here at all, we could just collapse the S stagger by unitarity, but this is really different. We can't do that here.
So it's a sort of cross section that you on which you integrate you use a sort of cross section to weight the fields that are in 3.
Exactly. The difference between this and a cross section is that 3 is not squared. So actually, so it's kind of an expectation value of something that's linear in 3. A cross section would always be quadratic in every particle. So that actually brings me very nicely to this 6-point asymptotic measurements, which include these kind of inclusive cross-section type of objects, along with scattering amplitudes and along with lots of other things. And for example, these are called out-of-time ordered correlators, where we have kind of a maximal scrambling of A's and B's. So we have A, B, basically. And in general, we can just write down at endpoints basically any string of S's and S staggers with some particles coming in and some particles coming out. And we can just count how many distinct measurements there are at endpoints. And we can see that it grows exponentially, like this 2 plus root 2 to the power of n, roughly at large n. So it actually turns out that scattering amplitudes are a very small fraction of the total number of observables at endpoints. But now you might ask, why am I writing this down? The cool thing is that it's actually, these observables, or at least some of them, have a nice physical interpretation. So of course, we know and love the scattering amplitudes. But for example, this expectation value that we talked about of a future operator in the background of other operators is something that we'll talk a lot more about in parts 3 and 4. It's the expectation value of the electromagnetic field in a scattering experiment, or the gravitational waveform as detected by a gravitational wave detector in the background of black hole scattering. So that's a new object that we can write down at 5 points that has also a physical interpretation and is an observable that's being measured. We already talked about how at 6 points there are inclusive cross-sections or inclusive particles numbers that are quadratic in the future operators. And then we can have also out-of-time ordered correlators, which are these scramblings between A's and B's. So now we've talked about how to write down basically these lots of different observables using the algebra of asymptotic measurements. So now we're going to talk a little bit about the computations and the physical properties of these different observables.
One question. The inclusive cross-section that you were talking before is somehow related. I mean, in this formalism, the usual separation that one does between the virtual part and the real part of the cross section comes automatically without making this separation, the usual separation of adding one part more. I mean, in the real correction is there.
Yeah. So here we would have basically. We would be fixing, for example, in this type of inclusive cross-section, I mean, you could write down different things. But yeah, you could write all of those contributions in this SS dagger form, for sure. So here, for example, we would have basically all types of radiation, real radiation that can be in the state X would be part of this observable here, while the virtual one would be contained in the SS or S daggers over here. But here we're not saying anything specifically about real versus virtual or infrared finiteness or anything like that. We're just saying that we can fit all of these observables into this kind of pictures and the operator algebra, the measurement algebra, basically. So depending on what you want to do, if you want to measure the real radiation or if you want to sum inclusively over it, etc., you would put different things here. But the important part is just that the framework can capture the different contributions.
I mean, all observable that usually one wants to extract from the radiation at classical level can be rephrased in this form.
Exactly. All of the observables that we can write basically as
like
these...
momentum, energy of the fields.
Yeah, so then we would start putting in some operators here at infinity, right? We would, for example, put in some momentum operator here or some measurement operator. But here we're kind of classifying the observables that can be written down using measurements in the past and the future, if that makes sense. Okay, so let's talk more about these types of observables. So let's talk about this waveform observables. So what's happening here is that we have basically a scattering of two black holes, for example, in gravity, that we've labeled with 1, 2, and 1 prime, 2 prime. And we then measure a graviton in the future. So let me emphasize that this is a very different type of measurement from what we do for scattering amplitudes. Because for scattering amplitudes, let's say we measure them at the Large Hadron Collider at CERN, then our detector, at least as close as possible, tries to measure all outgoing particles. So the way I imagine it is that it's almost like a spherical or as close to a spherical detector as we can achieve. And we try to measure all of the outgoing particles and their energies and momenta and their types, etc. But in a gravitational wave experiment, we have a very different situation because we don't have access, we don't have a spherical detector that surrounds the universe. So rather what happens is that there is some black hole scattering somewhere in the universe, and the only thing that we measure here on Earth is this graviton in the future. But then there was lots of other things happening and lots of other radiation going off in different directions, and that we just have to sum and integrate over in our observable. And that's why this observable represents the measurement of a gravitational field in the future. In the background, it's kind of, yeah, like an expectation value in the background of black hole scattering.
But the fact that these black holes are in, I mean, what? Of course, I can make change of basis and go to out, but what is the utility to express everything in terms of in states?
Oh, I mean, that's just what we usually do. We just use a basis of states. I mean, I think that's maybe what you're asking. I mean, we could use the out basis as well. It doesn't matter. It's just the S operator takes us from the past to the future. You can write it as an overlap of in or an out state, or you can write it as an in state S operator in state, basically. So that's just a notational convention, I would say. But it is important here, though, that we measure the graviton in the future. And causality is important there, that it's in the future of what happened here for the black holes.
I mean, the graviton in the future, but with background like in states. I mean, this is done because the physical interpretation is easier, or is it just?
I mean, whether you work in the basis, so in states or out states, doesn't matter at all.
Doesn't matter.
But that's just a choice of basis. But it does matter here that we're measuring, as I say, we're measuring something in the future happening, but the scattering kind of happened in the past, if that makes sense. It's in the future of this process.
Okay.
But yeah, I mean, we could absolutely write this in the basis of out states, and the expression would look a bit different, but it would have the same physical interpretation, and we would do the same computations. But anyway, so now we can write this out using that the S matrix is 1 plus I times the delta function times the matrix element n. And as we expand out these two terms, we actually get two contributions to the waveform. And this is just our choice of expansion, and this is still non-perturbative and everything. But we get the scattering amplitude for black holes to scatter to a graviton and two black holes. And then we get plus this cut term here, where we have basically an amplitude for black holes to graviton plus anything, and then that anything scatters through the conjugated element to black holes. And how do we compute these asymptotic observables? We actually have three ways of computing them. We can compute them as sums of amplitudes and cut amplitudes. We can use a generalized LSZ formula, or we can use analytic continuations. And this is supposed to be part 4 of the outline. Let me actually, because I want to rather spend more time on crossing, let me go very quickly through this part. I've already kind of shown you that we can break things up into amplitudes and cuts. And recall that as we do so, X is the complete set of states that we integrate inclusively over phase space. What we also have in our paper, and I'm not going to go through in detail here, is kind of this method 2, which is to use generalized LSZ. And again, we want to measure the field of a graviton in the background of black hole scattering. And it's very important that the graviton is measured in the far future. And using nonlinear response theory, we can represent this by a retarded function. And what's nice about that is that we can actually go through and use our favorite quantum field theory methods. And this is one thing that we can do in the classical limit. So there's been a lot of work on this in the past couple of years.
So, excuse me, the retarded function are those of Schrödinger-Keldysh? Are those
exactly.
are the
exactly.
commutator?
Exactly. So we get back to kind of an observable on a Schrödinger-Keldysh contour. So that observable kind of has this time-folded contour where the graviton is in the future, but then we have this kind of back and forth evolution. And we get exactly back, the Schrödinger-Keldysh representation.
Like when one compute the in state by the in formalism, the cosmological correlators.
Exactly. This is just an in and observable. It's nothing different. It's exactly what you're saying. Anyway, so I wanted to mention this observable a little bit because there's been a lot of interest around it. And what we want to do is that we want to take the classical limit, so to one loop order in perturbation theory. And now, again, all of the relations that we have hold non-perturbatively, but we're free to expand out in perturbation theory. So at one loop, we have these types of diagrams in the classical limit where two black holes go through. And interact in different ways. I've drawn some examples of diagrams here. There are, of course, many others that you can draw at this order. But the important thing is that there is a graviton emitted, and we have to take into account all the different ways in which we can place this orange cut, and one of them being this cut diagram where the graviton is emitted and crosses the cut to the future. So we now have to, in the classical limit, expand both the propagators and the cut terms in large values of the masses. And what happens is that the amplitude on the Schwinger-Keldysh contour...
But you need the Lagrangian for this.
Yeah, so here this is building upon this body of work from starting with Kosover, maybe, and O'Connell in 2018. And it's basically extracting the classical part of this observable using quantum field theory methods.
But I mean, starting from a Lagrangian with vertices
exactly.
and stuff. But exactly. If one wants to instead to use little group methods to compute the amplitudes, somehow this what you did should be extended also there, no?
Absolutely. It's just this is the current best method that we have to compute these things. But yeah, as I say, it shouldn't matter, especially for the crossing story. But here it turns out that the best we can do at this point is to expand it out in perturbation theory. But what I wanted to tell you is that this time-folded observable, or the Schwinger-Keldysh contour in an observable, whatever we want to call it over here, or the waveform, has different analytic properties than the amplitude. So we have to use this folded time contour. And what happens in these calculations that I wrote down, these propagators in perturbation theory, is that what used to be a Feynman propagator for the amplitude changes into a retarded propagator, as required by causality. So it's very nice to see that working out. So that's one avatar of kind of working with this different type of observable. The other avatar is that there's a different infrared divergence of the waveform compared with the amplitude. So there's a modified IR divergence due to basically two sources of Shapiro time delays. One delay is from the graviton escaping the classical gravitational field. And this one is very easy to understand. It's basically the usual redshift as the graviton is moving along to future infinity, but it still knows about the classical gravitational field of the black holes that are still there in our spacetime. But there's a different source of infrared divergence that we label with 2 or in blue. So that's a delay or an advance from the two black holes approaching each other and scattering basically earlier or later than anticipated from classical motion. So this is very easy to understand in the non-relativistic limit, because let's say we send in two black holes with some velocities, then if there were no infrared divergences, if there were no long-range interactions, then we would just expect that until they're very close to each other, they just move on their straight trajectories. But in the non-relativistic limit, the two black holes, because gravity is attractive, will approach each other. So they'll actually scatter earlier than we expect from them just going straight. And this earlier is actually logarithmically divergent in their separation distance. So there's basically these two sources of time delay that translate into the infrared divergence of the gravitational waveform. And let me actually skip the details and just tell you this in words, and we can go through it later. But the takeaway points from the talk so far is that the S matrix is only one of exponentially many asymptotic observables. And these asymptotic observables can be computed analogously to scattering amplitudes if we just use the time-folded or Schwinger-Keldysh contour. And in the rest of this talk, we'll talk about how to relate asymptotic observables to one another via analytic continuation. So we'll kind of come back to what we talked about in point 1. If you remember, where we talked about crossing symmetry, we kind of did this toy model tree level example where we saw that we landed on some different observable than the S matrix or the conjugated S matrix. So then we went on in 2 and 3 to talk about what are these different I epsilon prescriptions doing for us. And what they're doing for us is that they're putting the objects on a different time-folded contour. So we're actually able to capture not just scattering amplitudes, but also exponentially many other different asymptotic observables. And then we talked a little bit about their physical properties and how to compute them. And now we're going to talk again about how to relate them by analytic continuation.
Wait a minute. I mean, the prescription on the cuts were coming from the construction you did before, not from the modification of the contour. No, so, I mean.
Yeah, so you can use either, actually. So as I say, we have these 3 ways of computing them. So the first way is just to brute force it and write it out in terms of scattering amplitudes and cut amplitudes. But in practice, what's actually much easier to do is that basically, if we compute them in the traditional way of using differential equations and tensor reduction, etc., then we can simply impose different boundary conditions that capture the different time-folded contours. So basically, all our methods for computing scattering amplitudes don't know that there are scattering amplitudes until the very, very end when we put in boundary conditions. So all our techniques of tensor reductions, differential equations, integration by parts, etc., all of that doesn't know about the integration contour. So it's only way in the end when we impose the boundary conditions that we actually nail down that it's a scattering amplitude. And that's why we can also just use that very last step to nail down that it's not a scattering amplitude, but rather a waveform or maybe some other observable.
So, I mean, you want to say that you are replacing not the usual Feynman propagator, but the retarded function that the reduced propagator that
exactly
coming from the commutator, not from the T product.
Exactly. Oops, I'm going in the opposite direction. Sorry. Okay, so let's talk about part 4, which is
in part 3, the sigma where the contour shift the blade is a space-like surface at infinity.
Yeah, so it just has to be kind of after the emission of the graviton somewhere.
But so at infinity.
Yeah, at infinity.
I mean, because if one want to do final temperature, I mean, one could put sigma at finite time, no?
Yeah, so as I say, it's kind of a limiting procedure. But I mean, here, first of all, it's not a finite temperature system. It's a bit different. But it's a similar kind of time-folded contour that we put the sigma somewhere after the emission, and then the contour kind of turns around and the time goes in the other direction. Exactly. But I mean, as I say, it's if you're familiar with the Schrödinger-Kelder story, it's exactly the same. So it's nothing new.
But I mean, usually with at least what I have done by Kaldish Schwinger, there is it is not always mandatory to insert a system, a complete orthonormal system of states. One can do, for instance, somehow a sort of perturbation theory where this folded contour is implemented also without the insertion of intermediate states, no?
Yeah, absolutely. And as I say, let me think.
There are
I'll
this
get
paper
back to
of
that point.
Weinberg. There is this paper of Weinberg about cosmological correlators,
Yeah.
in which or like in condensed matter people that the usual make a unitarity transformation of the fields, and so they enter in the perturbative series, also without the insertion of intermediate states, no?
Absolutely, yeah. So, I mean, here, as I say, I think I'll talk about a little bit in part 4 how we practically compute them, because, as I say, it's really nothing. There's no more complexity than for scattering amplitudes.
Okay.
And that's so we'll get to that, and that's actually a cool part of the story, because these analytic continuations, they're precisely telling us that these objects are all on the same footing. So there's nothing more complicated about observables on the Schrödinger-Keldysh contour. It's just a different type of contour. And let's go to part 4. So what we do for the crossing is that we propose an on-shell contour of analytic continuation, which exchanges the incoming and outgoing states with a parameter z. So you might remember that way in the beginning of the talk, I had this complex z-plane, and we can now know what this z is. It's basically in light cone coordinates. We take one of the particles that we want to cross, let's call it little b, or if we want to cross many particles, we take them to be in the set capital B. And we take them to have a large plus component and a small minus component in light cone coordinates. And similarly for C, which would be the outgoing state that we want to make incoming, we take it also to have large plus component and a small minus component. And then we take the Z and rotate it in the complex plane from positive to negative. And note that this keeps all particles on shell at all times during the rotation, because p squared is just the plus and minus components multiplied minus the perp squared. So the z and 1 over z cancel out. And we can kind of use these colorings to probe what happens to the different Mandelstam invariants. So the uniform ones, the ones that have a uniform color, they stay fixed. But the ones that have a mixed color, like this 1,3, this S13, they're the ones that actually rotate during the analytic continuation. So here is the crossing equation for two-particle crossing, meaning that we have one incoming particle that we want to cross with one outgoing particle. So after we do that, we get this object here. And note that it's almost like a conjugated matrix element, but we have to correct it with these S blobs on the ends of the other incoming and other outgoing particles that we call A and D. There's a minus sign in front of the whole thing, and it simply comes from this I in the definition of the scattering amplitude. So you don't need to worry about it. It's something that comes out very naturally. One thing that I wanted to discuss is basically that at 2-to-2 crossing, this just goes back to the conjugated amplitude. And why is that? It's because of stability. So if we just have one particle here in A or one particle in D, what happens is that those particles can't evolve to anything. So we have to take basically this S blob to be just one. Nothing can interact for these particles. Let me mention the evidence that we have for this proposal. The evidence is basically loop level examples and tree level proof. And again, as I said in the beginning, we checked this for all master integrals relevant for 5-point scattering and one loop. And we'll get to that in a moment. But then we also have an argument from axiomatic field theory. If we assume that the path of analytic continuation exists, And what happens more practically is that we can take two of these operators, one a future operator and one past operator, one creation annihilator and one annihilation operator, and the crossing kind of changes the undaggered ones to be daggered and vice versa. So basically writing this out for this process here gives you this picture on the right. And let me go here. But it's also very important that we assume that the path of analytic continuation exists. And this can be very, very subtle. So we have actually a whole section in our paper devoted to this. Basically, we might need to continue past anomalous thresholds. So this is entirely expected from axiomatic field theory. But basically what happens in practice is that we have to take a large enough arc in this complex plane. We have to go to high enough energies, do the analytic continuation there, and as we continue down, we might have to wiggle away some thresholds to actually get to the correct value. So here, the red value is the correct one after the analytic continuation for this triangle diagram here. And the blue value, which we would get from basically doing the analytic continuation at low S, would not be correct. So once we use these crossing relations, we can basically relate these different asymptotic observables to each other. And we can divide them into families of who can be analytically continued into each other or not. So for example, starting with the S matrix at 6 points, so the 3-to-3 scattering matrix, we can get to all these different observables by using different crossing moves. And we don't yet know whether, or maybe more precisely in which cases, there exists continuations that continue the different families together. But note that we just need one link. So if we had one link from anyone in this family to anyone in this family, then all of the ones could be analytically continued into each other. So let's now revisit the tree level example that we had way in the beginning. And we're now going to be able to understand via the crossing equation what happens. So remember that we had this tree level example 1, 2 going to 3, 4, 5. And we started with a scattering amplitude where S13 was negative, so we don't have to attach an I epsilon. But S45 has a plus I epsilon because it's positive. We can now use our analytic continuation path in the Z's that we presented before. And S13 will rotate in the lower half plane according to that path, and S45 stays fixed. So that's one way, that's basically one way of computing what happens after crossing. But now we can check our crossing equation. So the prediction is that we have to fit this diagram into this blob picture in all different ways. So one thing that we can always do is that we can place this whole picture in the S dagger blob in the middle and just take the S's here to be 1 on the outside. So then we get back the conjugated amplitude. But now we have a different way of fitting this into this amplitude because 4, 5 are the outgoing particles in the D. So we can have something happening in this blob S here. So we can basically place these particles on the orange cut to get back precisely the cut term. But then there are a lot of different patterns that are disallowed for different reasons. For example, 1 and 3 cannot interact before the cut. So we cannot write down this amplitude here. And this one is basically disallowed by energy conservation because we can't have this blue energetic line going back and forth between this cut here. But in any case, we can now compare what we had on the previous slide, which was doing the analytic continuation and the prediction from the crossing equation. And we can verify the crossing equation for this example. And this is what we've done in more complicated examples. We checked basically all d-dimensional massless basis integrals for an expansion around d equals 4 for 5 points, which amounts to checking all bubbles, triangles, boxes, and pentagons. And then we have a proof at any multiplicity at tree level. And again, this might sound trivial, but keeping track of the combinatorics is actually highly non-trivial. And yeah, so that's what we have in our paper. But let me just show you that for the pentagon, this is really a non-trivial check. So here is basically, if you're familiar with the differential equation methods, this is what we could use to compute the pentagon. If you're not, that's fine. But the only takeaway point here is that we can check the crossing equation for these diagrams, for basically all diagrams in this family, by basically comparing these three matrices. And if we were to stop at this slide for much longer, you could actually check that this matrix minus this matrix plus this matrix gives 0. So the last slide before conclusions is to recall that we talked a lot about the waveform as measured in gravitational wave experiments from scattering of black holes is obtained as an Indian expectation value. And we can compute it either via this modified LSZ, via summing amplitudes or cuts, but now we actually have a new method. We can analytically continue the 5-point amplitude, but it's kind of a crazy object to start with. And this might be reminiscent of the example from the beginning where we had an Earth anti-Earth to apple anti-apple, because the object that captures the expectation value of this gravitational wave is basically a hard graviton scattering against a black hole, a very, very energetic graviton scattering against a black hole to produce black hole, anti-black hole. So that's something that we tried on a couple of examples. But the unfortunate thing, the caveat is that, of course, this goes way out of the classical limit of this observable, because in the classical limit, we take this graviton to have very low energies, but for the crossing, we actually need the graviton to be very energetic. But in any case, it's a different way to compute it. So that brings me to my conclusions. We talked about how there are exponentially many asymptotic observables, for example, gravitational waveforms, out-of-time ordered correlators, and Indian expectation values. And then the punchline is that via new versions of crossing symmetry, we can show that the S matrix contains this host of asymptotic observables, which are related by analytic continuations between different channels. So for example, we had way in the beginning this process of E minus gamma going to E plus E minus, and we now know what's the analytic continuation of that process. It becomes this expectation value of the photon in the background of electron scattering. So with that, let me thank you a lot for coming, and I'm happy to take more questions.
Okay, thank you so much. Amazing, really joyful your talk. Thank you so much.
Glad to hear that. Thanks for your questions.
Now for questions, also in Spanish, as you want, but please. Edison, please. So, Edison is a...
Can you hear me well?
Yeah,
Edison,
I can hear you well.
Is a three-loop man. So, I mean, he has a lot of experience with analyticity properties of
Indeed.
Yeah, please.
Okay, thank you, Hofie, for this quite interesting talk. I have a general question. All the examples you showed were for one loop level or for tree level, right? But can these crossing relations be used in diagrams with two or higher loops to relate observables?
Excellent question. Let me make a few comments about that. So first of all, we are working on a proof, but we don't currently have a proof non-perturbatively. But we have basically an argument from axiomatic field theory. And the argument basically, if we go back to this, let's see now. If we go back to this picture here, yes. The argument that we have basically assumes that we can go to high enough energies so that we don't cross, so that we don't encounter any singularities. So it's basically using the same proof as this proof here, except applied for 2 to 3 particles. However, we know that there might be some special cases in which there might be singularities on the way that obstruct this. So that's precisely what we're trying to figure out. Basically, what are these edge cases which we might encounter so that it doesn't hold generally. Interestingly, taking all particles to be massless seems to be a good thing in this story. So the place in which we were encountering subtleties was basically processes like this one here, where the internal mass is exactly the same as an external mass, and we have a massless particle in the loop. So from axiomatic field theory, we have this kind of space-time interpretation, and we have an argument for when things hold and when things go wrong. And the short story is that we expect things to hold in a very general situation. But yeah, we're working on a full-fledged proof of it. So we definitely expect it to hold at higher loops, but we didn't go through the trouble of checking it because we rather wanted to focus on kind of proving it once and for all, if that makes sense.
Okay. I have another question. I didn't get something. Is it always possible to relate an observable to any other observable using crossing relations, or
right now we don't know. We don't know whether it's always possible or not, but we don't know how to do it currently. So with the crossing moves that we have right now at our disposal, basically, for example, at 6 points, we got these different families, meaning that we don't know whether there exists an analytic continuation between them. It's here, I think, yeah. So we can do an analytic continuation basically between any 2 objects within family 1 or family 2 or family 3 separately. But we don't know how to go from, let's say, can you see my mouse or no? Probably not.
No.
Yeah, we don't know how to go from, say, the scattering amplitude in 1 to something in family 2. So there might be that there's a different path of analytic continuation from the one that I presented in the Z's that gets you there. So we definitely don't have a proof that it doesn't exist, but it would have to be something different. So the crossing path that we know right now kind of, has these 3 different families. So not everything can be continued into anything else with this crossing move.
Okay, thank you.
Yeah, you're welcome.
More question for Hofie? Daniel, who is a black hole man. Christian, please. So you wrote the answer. So you wrote, in the case of a black hole, a V-scalar, that is its own anti-black hole, can you conclude it is a Schwarzschild black hole?
Yeah, I would say I'm not sure whether that's always true. In these computations, of course, we're simplifying our lives a lot by taking these black holes to be heavy scalars and kind of modeling them in that way. And if you don't do that, or if you do different things, it's not my expertise exactly what happens, and there's a lot of ongoing work about it.
At some point, Christian Santiago said, at some point you mentioned, at some point you mentioned the use of nonlinear response theory, the retarded function. This term, this means the use of higher perturbative terms of a linear response theory, means the linear response theory of Kubo in condensed matter, or is a different prescription for their computation?
No, this is precisely what people use in condensed matter. It's and that part is not really related to the crossing story, and as I say, it's not new prescriptions in any way. So I just wanted to point out that this is an alternative way for, yeah, as I say, we have these three different ways of computing these objects, and one of them is the linear response theory, putting things on a Schwinger-Keldysh contour, and it's just standard textbook formulation.
Mm-hmm. And the other question: can we compute the decay with of 1 to n process from a cross section n to 1 via analytical continuation?
Yeah. So here we could just use, if I understand the question correctly, we could just use CPT to relate a 1 to n process to an n to 1 process. We might ask a different question, which is, can we compute the decay with 1 to n from a different scattering amplitude, let's say 2 to n minus 1 or something like that. And there, what I would try is that I would try modeling kind of the decaying particle as two particles and putting that into the crossing relation. Yeah, basically modeling it as two incoming particles instead of one, because these relations always assume stability. And then we would have to go to our families and ask whether that would be possible.
Yes. So, more questions for Hofie? And I mean, the use of axiomatic field theory, in that case, usually, I mean, in the traditional books of axiomatic field theory, there is always the mass gap. So in your case, that you don't have, you have also massless particles. How do you use the axiomatic field theory?
Excellent question. Short answer is that it's still a very pressing, in my opinion, open question. Long answer is that in axiomatic field theory, we always have to have a mass gap. Things blatantly don't converge if we have massless particles for many reasons. And as I was saying in the beginning, for example, in the 2 to 2 proof, it's absolutely crucial that we have a mass gap, because otherwise this shaded region just goes to infinity. For us, as I say, one thing that we wanted to do, and the reason why we did these one loop checks, was precisely because of massless particles. It was precisely because we don't have a handle on them in axiomatic field theory. So we just thought, okay, let's just go ahead and compute it and try and see what happens. And everything worked out very nicely. And so naively at this point, it doesn't look like massless particles are a hurdle for us. But yeah, I mean, it's definitely one of the big open questions in this whole field, is how to incorporate massless particles and if there are subtleties with that. So the way we did it was just in dimensional regularization, so that things are well defined. And then we were not summing over real and virtual or anything like that. We were just taking the amplitudes and the other observables on the nose as the dimensionally regulated answer. And crossing worked in, as I say, in all cases that we tried, basically in any dimension for this pentagon family.
So in practice, one of the strong message of your talk is that everything is based on S matrix.
Yes, or maybe that the S matrix contains so much more than we thought. So that's why I got so interested in this, because I thought it was amazing that we have, I mean, we measure things on a tiny slip of the real axis, but then it knows about this whole host of other observables as well. So I think that was really a surprise to me.
So I mean, even if there are theorems from the ancient time that all expectation values in endowed states can be expressed in terms of S matrix, where the operator that you compute the expectation value are coupled to sources with respect to you make functional derivatives. So the S matrix is the basic quantity, and the fact that the calculation of observable arises because analytical continuation of S matrix elements is really amazing. So something
Thank you.
extremely exciting.
Yeah, and let me also mention another maybe potential application. So there has been a revival of the S matrix bootstrap, and their crossing is kind of built into the first step. It's built into the ansatz that people bootstrap. So basically, knowing this picture here that I drew away in the end, where is it? This one here. That's basically a starting point if we want to push, the non-perturbative kind of numerical bootstrap computations for the S matrix to higher multiplicity. So for 2 to 3 scattering or 3 to 3 scattering, etc. If we want to do that, then we need to know in the first place how the scattering amplitude behaves in the complex plane. So that's also why I got excited about this, is because it kind of gives a starting point, at least. Maybe we're still far away, but it gives a starting point for the for bootstrap in for 2 to 3 or 3 to 3, etc.
But also, I mean, at the start you said that you don't care about the numerator. But since there are blocks of S matrix with on-shell particle attached, I mean, the cuts are not just diagrammatically, are at the level of amplitudes.
Absolutely,
and
100%.
And so the numerators are important.
Absolutely,
Because they will provide amplitudes. So, for instance, let's say if you cut a plus and minus with a photon, a cut on the photon, that residue is zero because I mean there is no momentum conservation. I mean, so the numerator it's important in this.
It's absolutely, yeah. I certainly didn't mean to imply that it was not important. It's just the reason why I'm not worried about it is because it's so much easier to incorporate the numerators than the denominators, if that makes any sense. So at a technical, it's absolutely 100% important. For the physics, it's of course entirely crucial. But for the mathematics of deriving these relations, it's much simpler to include the numerator than it is to include the denominators, if that makes sense.
And so if one want to jump in this business, it's mandatory to start also from this paper of the 60s.
Good question. I mean, I hope our paper is easier to start with. And one thing that we did was in the appendix that we summarized these proofs, hopefully in a bit less technical language, in a more physics-inspired, a bit less rigorous, but more, at least to me, more understandable way. Otherwise I would recommend starting, I guess, with lecture notes from the 60s. But it's a bit, I mean, there has been a lot of revival, and there is.
But let me actually these famous lecture notes of Martin.
Yeah, exactly. And Summer, there's a paper from summer from 1970, which is like a summary of what had been going on. And it's also good because it was, like at the end of it. So if you start reading some of the earlier papers, it's very easy to get confused because people were very confused.
No, for sure.
And then things got kind of sorted out. But yeah, I mean, there's a lot of good, very recent resources, I think. So I think it's going to also get much better. And I was referring to these papers, of course, because this work specifically built upon it. But I think we also kind of want to get away from it because I think they were very smart and did everything that I think they could at the time, if that makes sense. So I think also we need new ideas to push it forward. So, but people should judge for themselves, and
Yes.
but I think that's my point of view. If there was some low-hanging fruit, they would have written it down at the time, I think.
Okay, so thank you so much
thanks
for the great effort that we have done for us, and we have learned very much.
I'm glad to hear that. It was a pleasure.
I hope we can stay in touch and exchange ideas about
100%.
About the subject. So thanks again, and
thanks everyone.
And let's keep in touch.
Absolutely.
So, gracias a todos. Bye. Ciao. Gracias a todos.
Ciao.
Thank you so much.
We will see again next in 2 weeks with the PRST talk. Bye. Ciao.
Bye.